Right now, in the silent depths of space, something extraordinary anchors our entire galaxy. A monster so immense that 4 million suns would barely match its mass, and so compact that it bends time and swallows light. Tonight, we will journey to the center of the Milky Way to finally discover just how big Sagittarius A star truly is. If you enjoy these cosmic explorations, please like this video and subscribe to the channel. But pause for a moment and wonder, how big is a black hole that controls the orbits of 400 billion stars? How does time falter at its edge? Could something so invisible truly hold the galaxy together? And what secrets still hide within its shadows? Stay with us as we drift across 26,000 light-years of space toward the very heart of the Milky Way. Let's begin. In the direction of Sagittarius, behind vast curtains of dust and gas, lies a point of gravity so powerful that it shapes the Milky Way itself. This is Sagittarius A star, a gravitational anchor that has remained invisible for most of human history. For centuries, humanity gazed toward the center of the night sky and saw only darkness. Even the most powerful optical telescopes could not pierce the dense veils of interstellar dust that stretch across the galactic plane. The core of the Milky Way remained hidden, like a candle burning behind a thick curtain. To ancient astronomers, the band of light we call the Milky Way appeared eternal and unchanging, a river of stars flowing across the heavens. Yet beneath that shimmering arc, in the constellation of Sagittarius, something colossal waited patiently to be discovered. Our solar system drifts 26,000 light-years away from this hidden giant. To us, it appears as just another patch of sky, filled with star clusters and nebulous clouds. But behind that familiar scenery, in a region invisible to human eyes, lies the most massive object in our galaxy. A singular source of gravity so immense that 400 billion stars orbit its unseen presence. Imagine for a moment the enormity of that number. Every star you've ever seen in the night sky, every star in our spiral arms, every cluster and cloud of light, all of them moving under the influence of a single anchor, a single point of unimaginable density. The concept seems impossible. How can something so massive, so influential, remain hidden? The answer lies in the nature of light itself. Dust absorbs and scatters visible light, smothering our view of the galactic core. For generations, astronomers were blind to what lurked there. It was not until the 20th century that radio telescopes, instruments that listen instead of look, finally began to peel away the fog. Through radio waves, scientists detected a compact source of energy at the galaxy's center, brighter in its frequency than anything else around it. They gave it a simple, almost understated name: Sagittarius A star. The asterisk at the end was not a flourish, but a marker. It denoted a source so unusual that it demanded attention, a mystery waiting to be solved. What kind of object could generate such intense radio waves while remaining invisible in every other spectrum of light? Over time, careful observations revealed a disturbing truth. Whatever lay there was not a star, not a cluster, not a glowing cloud of gas. It was something far stranger. Sagittarius A star is a supermassive black hole, 4 million times heavier than our Sun, and yet compressed into a region so small that it could fit inside the orbit of Mercury. No light escapes it. No information returns from beyond its event horizon. Its presence can only be inferred from the way it sculpts the orbits of nearby stars and stirs the matter that falls too close. It is the silent conductor of the Milky Way's grand orchestra, unseen but in absolute control. Tonight, as we continue our journey, we will step closer toward this hidden heart. We will explore how it bends time, how it shapes orbits, and how, after centuries of searching, humanity finally managed to glimpse the monster behind the curtain of dust. But for now, Let us pause with the wonder of knowing that deep within the Sagittarius constellation, at the place where our galaxy gathers all its weight, an invisible giant holds everything together. Astronomers discovered that the central object must weigh the equivalent of 4 million suns, yet fit inside a region smaller than our solar system. No star or cluster could survive such conditions. Only a black hole could. This conclusion did not come easily. For much of the 20th century, astronomers debated what could possibly reside at the galaxy's core. When they first observed stars near the center, their behavior seemed bizarre. These stars raced across the sky, not drifting lazily as most stars do, but tracing tight, rapid paths as if tethered to some invisible anchor. Something enormous was pulling on them, but when telescopes searched for the culprit, they saw only darkness. To understand the scale, imagine the Sun. It holds 99.8% of all the mass in our solar system. Its gravity keeps Earth's orbit stable, guides Jupiter's moons, and controls every comet and asteroid that wanders through our cosmic neighborhood. Yet compared to Sagittarius A star, the Sun is almost weightless. Multiply its mass 4 million times, crush that unimaginable weight into a space smaller than the orbit of Mercury, and you begin to approach the reality at the heart of the Milky Way. No ordinary object could survive such compression. A cluster of stars would collapse under its own weight. A ball of gas would ignite in a furious blaze long before reaching such density. Even the densest neutron star, made of tightly packed atomic nuclei, would collapse into nothingness. Only one possibility remained. A black hole. A region where matter falls inward until gravity becomes absolute. The numbers became clear thanks to one particular star, known as S2. Every 16 years, this bright blue giant completes an orbit around the galactic center. At its closest approach, it swoops to within just 120 astronomical units, a cosmic hair's breadth, and rockets forward at 17 million miles per hour. By carefully tracking S2's orbit, astronomers could weigh the invisible mass with incredible precision. 4.297 million solar masses, accurate to within just 12,000 suns. The result left no doubt. Think of what this means. Our galaxy, with its spiral arms stretching 100,000 light-years, with its vast seas of gas and dust and billions of stars, is held together by an object no larger than a star system. It is as if the entire Milky Way is a great wheel, and Sagittarius A star is the axle at its center, unseen but indispensable. Without it, the galaxy would unravel. With it, every orbit finds its balance. It is almost paradoxical. Something so small compared to the galaxy it governs holds such overwhelming power. 4 million suns crushed into silence, shaping the destiny of 400 billion others. A monster, invisible and patient, waiting at the center of everything we know. And yet, the proof of its existence is not only written in mathematics, it is also visible in motion, in the extraordinary dance of stars that whirl around the void. That stellar ballet is where we will turn next. Near the galactic core, certain stars move in frantic orbits. Their paths curve around nothing visible, yet their motions reveal the presence of an unseen mass. These stellar dances became the cosmic scales that finally weighed Sagittarius A star. For most of the sky, stars drift so slowly that their movement is imperceptible over a human lifetime. But deep in the center of the Milky Way, astronomers noticed something startling. A handful of stars were racing across the darkness, tracing long, looping ellipses around an apparently empty patch of sky. To see these motions at all required decades of patient observation. Teams of astronomers returned year after year, capturing the faint glow of the same stars and mapping their positions with exquisite precision. Over time, the illusion of stillness broke, and the orbits revealed themselves. What they discovered looked less like a peaceful drift and more like a cosmic racetrack. Stars in this central cluster did not wander randomly. They all seemed to be pulled by an unseen anchor at the exact same point in space. Some took centuries to complete their paths. Others, like the star S2, orbited in just 16 years, a blink of an eye on cosmic timescales. At closest approach, S2 hurtled forward at 17 million miles per hour, a speed so fast it could cross the distance from Earth to the Moon in less than 3 seconds. To astronomers, these orbits were more than a spectacle. They were a measuring tool. The shape and speed of each path provided a precise calculation of the mass that must sit at the center. Newton's law of gravitation, refined by Einstein's general relativity, leaves no ambiguity. If you know how an object moves, you can deduce what it orbits. In this case, the math was unavoidable. The hidden anchor had to weigh millions of solar masses. But the stars revealed more than just mass. Their motions also eliminated other possibilities. If the central object were a dense cluster of stars, their combined gravity would tug and scatter each orbit over time. The paths would wobble, twist, or unravel. Yet decade after decade, the stars traced the same elegant ellipses, unwavering. This stability proved that the anchor was not many objects, it was one. A single, unimaginably compact source of gravity. The orbits also showed hints of relativity in action. As S2 swung closest to the center, its light stretched to redder wavelengths, exactly as Einstein predicted when time slows in strong gravity. The star's orbit did not close neatly on itself, but shifted slightly with each revolution, tracing a rosette pattern like the petals of a cosmic flower. Even in the chaotic heart of the galaxy, the stars whispered confirmation of general relativity's truth. And so, the dance in the darkness became a revelation. These stars, circling nothing visible, told us more than any photograph could. They pointed, unerringly, to the presence of a monster. A black hole weighing 4 million suns. The galaxy's deepest secret, revealed not by light, but by motion. One star, known as S2, races at 17 million miles per hour during its closest approach. Its orbit, repeated every 16 years, is proof that an immense black hole lurks at the center, warping space itself. To understand what makes this so extraordinary, we first need to put speed in perspective. The fastest passenger jet in history, the Concorde, reached just over 1,300 miles per hour. The International Space Station circles Earth at 17,000 miles per hour. Even Voyager 1, the most distant human-made object, travels at 38,000 miles per hour. S2 moves nearly 450 times faster than that. It is the undisputed sprinter of the galaxy, moving at such velocity that it covers the distance between Earth and the Moon in less than 20 seconds. S2 is a blue giant star, about 15 times the mass of our Sun. Under normal circumstances, a star of this size would live a stable, leisurely existence. But its neighborhood is anything but ordinary. It belongs to a cluster of stars that orbit dangerously close to Sagittarius A star. Its orbit was close enough, and its speed extreme enough, to reveal the true mass of the invisible anchor at the galaxy's center. Every 16 years, S2 completes its elongated loop. At its farthest distance, it drifts thousands of astronomical units away, but when it swings back in, it skims within just 120 astronomical units of the black hole. That's only 3 times the distance between the Sun and Pluto. Imagine the gravitational forces at work there. A star, hundreds of thousands of times larger than Earth, slingshotting around a point of space with unimaginable power. During its closest approach in 2018, astronomers observed something remarkable. The star's light stretched toward the red end of the spectrum, just as Einstein predicted. This redshift was not due to motion alone, but also to gravity itself pulling on the photons, draining them of energy as they escaped the black hole's influence. It was the first time this effect gravitational redshift had ever been confirmed in a star orbiting a black hole. Time, in those brief moments, was literally running more slowly for S2 than it was for us here on Earth. S2's existence also rules out alternative explanations for the central mass. If the core of the galaxy were made up of tightly packed stars or exotic objects, their combined gravity would not allow S2 to survive such a close pass. The star would be torn apart, or its orbit scattered into chaos. Instead, S2 follows a precise, predictable path, like a cosmic messenger pointing to the truth. Only a supermassive black hole could explain it. When we look at S2, we are not just watching a star, we are watching physics in its purest form, an object carrying out an experiment that no laboratory could ever attempt. With every lap it completes, it confirms the reality of the black hole at the galaxy's heart, a silent witness, forever circling the void. Einstein predicted that strong gravity slows time. Near Sagittarius A star, seconds stretch into eternity. For a star skimming close to the black hole, time runs just a little slower than for us here on Earth. This idea, once purely theoretical, is now confirmed by observation. Time does not flow at the same rate everywhere in the universe. The presence of mass bends space, and with it, bends the passage of time itself. Here on Earth, we already experience this effect, though it is almost imperceptible. GPS satellites orbiting above us tick ever so slightly faster than clocks on the ground, because they are farther from Earth's gravity well. Engineers must correct for this difference, or the system would fail. If such tiny variations exist around our modest planet, imagine what happens in the crushing grip of a supermassive black hole. For the star known as S2, time itself becomes distorted during its closest pass around Sagittarius A star. As it races past the black hole at 17 million miles per hour, its light is stretched into longer, redder wavelengths. This is not just a Doppler shift from motion, but a gravitational redshift light losing energy as it climbs out of warped space-time. That redshift is direct evidence that time near Sagittarius A star runs slower compared to our own. To us, the star's clock ticks sluggishly, while to the star, nothing feels unusual at all. If you could somehow place yourself aboard S2 during this close encounter, the effect would be even more dramatic. But to an observer watching from Earth, you would appear to move in slow motion. The difference is small, but measurable, and grows more extreme the closer one drifts toward the black hole's edge. Einstein's equations predict that at the event horizon itself, time for an outside observer slows to a complete halt. Anything falling in would seem to freeze in place, dimming and reddening until vanishing from sight. Yet from the perspective of the falling object, time flows normally. The paradox is unsettling, a reminder that our perception of time is not absolute, but relative to the fabric of space itself. This bending of time challenges our most fundamental intuitions. We assume that a second is the same everywhere, that the tick of a clock is universal. But Sagittarius A star shows us otherwise. Time is elastic. It stretches and contracts depending on the strength of gravity. And the black hole at the center of our galaxy is one of the most powerful demonstrations of this truth. Every orbit of S2 is more than just a stellar race, it is a cosmic experiment, a natural laboratory testing the deepest predictions of general relativity. And each pass confirms what Einstein envisioned a century ago, that gravity and time are inseparably linked, and that near the edge of a black hole, even eternity begins to blur. In 2022, the Event Horizon Telescope revealed the very first image of Sagittarius A star, a glowing ring of light encircling a perfect shadow, a photograph of the place where space and time collapse. For decades, the idea of photographing a black hole seemed impossible. Its very nature is to trap photons, locking them behind an event horizon that no information can cross. How can you capture an image of something that is, by design, invisible? The answer lay not in photographing the black hole itself, but in capturing its outline, the shadow it casts against the glow of surrounding matter. Sagittarius A star is far smaller than many of its cousins in other galaxies. The black hole at the centre of Messier 87, for instance, is over 1,000 times more massive. That size makes it easier to observe, because the larger the black hole, the larger its shadow appears from Earth. Sagittarius A star, though massive by our standards, is still relatively tiny and shrouded by 26,000 light-years of gas, dust, and stellar radiation. Its image was expected to blur, distort, and flicker like a candle flame seen through stormy glass. The challenge was immense. To resolve something so small in the sky required a telescope effectively the size of Earth itself. Of course, no such instrument could ever be built. Instead, astronomers linked radio observatories across 4 continents, synchronizing them with atomic clocks to create a virtual Earth-sized eye. This network, known as the Event Horizon Telescope, acted as one unified instrument, sensitive enough to detect details as fine as spotting an orange on the surface of the Moon. Still, the task was not straightforward. Sagittarius A star changes constantly. The hot gas spiraling around it flares, dims, and swirls on timescales of minutes. To freeze its image, astronomers had to collect enormous amounts of data across multiple nights. Petabytes of information were recorded on hard drives, flown around the globe, and fed into supercomputers powerful enough to stitch the signals into a coherent picture. The process took years of refinement, with scientists carefully comparing models until a consistent image emerged. The result stunned the world. There it was, a glowing, turbulent ring of light, bent and magnified by gravity, encircling a perfectly black center. That darkness is the shadow of Sagittarius A star, the imprint of the event horizon itself. Around it, plasma billions of degrees, hot races in spirals at near light speed, emitting radio waves as it plunges toward oblivion. The image matched Einstein's predictions with eerie accuracy. A century-old theory had painted a picture of something humanity had never seen, and the universe confirmed it almost brushstroke for brushstroke. More than a photograph, it was a moment of confirmation. For the first time, humanity had proof that the monster at the heart of our galaxy was real, not just an equation in a textbook or an idea in the minds of physicists. It was a shadow made visible, a window into a place where time, light, and space itself are pulled beyond return. The edge of no return, called the event horizon, spans just 12 million miles. It sounds enormous, yet on the scale of the galaxy it is a tiny pinprick of darkness controlling everything around it. To imagine this size, let us compare. 12 million miles may seem vast, but our own sun is nearly 1 million miles wide. If you lined up 13 suns side by side, their combined width would equal the diameter of Sagittarius A star's event horizon. That boundary, that invisible sphere, is the ultimate point of no escape. Anything crossing it, light, matter, even time itself, is lost forever. And yet, for something so small, its influence is staggering. Our galaxy stretches more than 100,000 light-years across. 400 billion stars trace their paths in graceful spirals under its pull. From such a vast perspective, the event horizon is no more than a microscopic blemish, a mote of darkness at the very center. Still, this single point governs the fate of the entire Milky Way. If Earth somehow replaced one of those doomed stars skimming close to the black hole, our view of the event horizon would be surreal. The black circle would dominate half the sky, a hole punched through the fabric of reality. Around its edge, arcs of distorted starlight would bend, twisted by gravity into halos and crescents. Even from a safe distance, the sight would be both terrifying and mesmerizing. The ultimate frontier between being and nothingness. The event horizon itself is not a physical surface. It has no material edge, no glowing wall. It is a boundary drawn by space-time, the place where gravity becomes absolute. To an outside observer, anything falling toward it seems to slow, dim, and freeze in place. From the perspective of the falling object, however, it crosses without hesitation, slipping silently into the black hole's interior. This paradox is one of the strangest consequences of relativity. A clash of viewpoints that both remain correct, depending on where you stand. Though Sagittarius A star's horizon is immense compared to our solar system, it is tiny compared to other cosmic monsters. The black hole at the center of galaxy Messier 87 is 6.5 billion times the mass of our Sun, with an event horizon wider than our entire solar system. By comparison, Sagittarius A star is a modest giant, more intimate, closer to us, almost approachable in its scale. Yet the truth remains, size is deceptive. A sphere just 12 million miles wide contains 4 million solar masses, a pinprick of darkness that can hold a galaxy in its grip. It reminds us that in the universe, power is not always measured by size, but by density, by concentration, by the bending of space itself. When we speak of the event horizon, we speak of a limit, a border where our understanding breaks down. On one side, the familiar universe continues. On the other, a silence deeper than anything we can imagine. If you could drift closer, you would see space stretch and light bend. To you, the fall would feel quick, but to distant observers, your descent would appear to freeze at the edge of the shadow. This is the paradox of the event horizon. From your perspective, nothing unusual happens as you cross it. You would continue forward, watching the glow of the universe shrink behind you. But from the perspective of those watching from afar, your fall slows, your light grows redder, and you appear to hover just above the black circle. Eventually, your image would fade away, stretched into invisibility by the warping of time. You would have vanished from their universe, but for you, the journey would still be underway. As you approach, gravity would no longer act in ways we consider familiar. Near Earth, gravity simply pulls down. Near Sagittarius A star, it pulls not only on your body but on time and space themselves. Light curves around the horizon, bending into arcs and loops. Distant stars would smear into luminous rings, their images distorted like reflections in rippling water. You would no longer trust your eyes, for what you saw would not be reality, but the geometry of space-time, reshaped by the black hole's presence. Crossing the event horizon, nothing signals the transition. No wall, no boundary, no change in sensation. But once inside, escape is impossible. Every direction leads inward. Even if you traveled at the speed of light, you could not climb back out. The horizon is not a surface but a threshold, one that redefines the rules of motion. Deeper in, tidal forces grow overwhelming. The side of your body closer to the black hole feels a stronger pull than the side farther away. This stretching effect, often called spaghettification, elongates objects into thin threads of matter. For a small black hole, these forces become deadly well before reaching the event horizon. But Sagittarius A star is so massive that its tidal pull at the horizon is surprisingly gentle. You might cross it intact, only to be torn apart later as you draw closer to the singularity hidden at the core. What happens beyond that point remains the greatest mystery in physics. Some theories suggest you would be crushed into the singularity, a point of infinite density where the known laws of science collapse. Others propose that new physics emerges inside, perhaps even connections to other regions of space and time. The truth lies beyond observation, forever hidden inside the veil of the event horizon. For now, we can only stand at the edge and imagine. The shadow we see from Earth is not just a picture, but a boundary drawn across reality. On one side lies everything we know, galaxies, stars, planets, and life. On the other lies silence, where space and time themselves fall inward. To drift into that darkness is to embark on a one-way journey, not into death but into the unknown. Imagine a valley so deep that not even light can escape. That is the gravitational well of Sagittarius A star. Every particle, every photon that ventures too close, is trapped forever. Gravity wells exist everywhere. Earth has one. It keeps our feet planted firmly on the ground, holds our atmosphere in place, and guides the moon around us in its orbit. The sun has a deeper one, keeping planets tethered as they circle endlessly around it. But the black hole at the center of our galaxy is a well so steep that no ladder, no rocket, no beam of light can climb out once it crosses the boundary. It is the ultimate trap, a pit not carved into land or stone, but into the very geometry of space-time. Picture rolling a marble across a stretched sheet of fabric. A pebble placed on the sheet makes only a small dimple, pulling the marble gently toward it. Place a bowling ball, and the marble races inward more quickly. Now imagine compressing 4 million suns into a space no larger than a single star system. The fabric would not merely dip, it would collapse into a pit so steep that the marble could never return. For objects far from the black hole, the well's pull is subtle. Our solar system, for example, is influenced by Sagittarius A star, yet it does not feel overwhelming. Earth continues its orbit around the Sun, largely unaffected because the black hole's gravity is diluted over 26,000 light-years of distance. But as you draw closer to the galactic center, the gradient steepens. Stars whip around in tight ellipses, gas clouds spiral inward, and time itself slows relative to the outer galaxy. Everything responds to the invisible valley, everything sliding toward the dark center. The depth of this well can be measured. Photons, particles of light, climb out of it more slowly, losing energy and shifting toward the red end of the spectrum. This gravitational redshift was detected in the star S2 as it made its closest pass. The light we received from it carried the signature of a star shining from the edge of a cosmic abyss. Inside the well, physics itself becomes strange. For ordinary planets and stars, gravity acts like a guide, pulling steadily but predictably. For Sagittarius A star, the gradient is so sharp that different parts of an object experience vastly different pulls. This is why tidal forces stretch and squeeze matter, tearing it into ribbons before it disappears across the horizon. The well has no bottom that we can describe. Beyond the horizon lies the singularity, where density and curvature become infinite in our equations. It is not simply the floor of the valley, it is the collapse of the valley itself, the point where space and time end. From afar, though, the gravitational well is not destructive but harmonious. It is the hidden reason the Milky Way holds together, the unseen bowl in which billions of stars swirl like glittering grains of sand. Without it, our galaxy would scatter, its stars drifting apart into the void. The darkness at the center creates the beauty we see in the night sky. For centuries, the galactic center looked empty through optical telescopes. Dust clouds blocked our view. Only when astronomers tuned into radio waves could they glimpse the roaring furnace hidden behind the fog. The Milky Way, as we see it with our eyes, is a river of light stretched across the heavens. But this river is not clear. It is filled with currents of dust and gas, opaque to visible light. These interstellar clouds, spread across thousands of light years, act like a cosmic curtain. They scatter and absorb starlight, dimming what lies beyond. When Galileo first turned his telescope toward the Milky Way, he saw countless stars revealed in its glow, but even his sharp optics could not pierce the thick wall of dust at the galaxy's center. For centuries, astronomers were left staring into a dark, seemingly empty void. The truth, however, was that the void was not empty at all. Hidden behind the fog was the brightest, most energetic region in our galaxy. But to see it, humanity had to look with new eyes, not in visible light, but in wavelengths that can slip through the dust. Radio waves, with their long wavelengths, are barely disturbed by interstellar clouds. They pass through like whispers through walls, carrying with them the secrets of the galactic core. In the 1,930 seconds, Carl Jansky, working at Bell Labs, detected mysterious radio static coming from the direction of the constellation Sagittarius. It was one of the first hints that the galaxy was speaking in a language beyond visible light. By the 1,970 seconds, with radio telescopes aimed at the galactic center, astronomers discovered something extraordinary. A compact source of radio energy brighter than anything else in the Milky Way. They called it Sagittarius A star, marking it with an asterisk to note its unusual nature. Still, a mystery remained. While radio waves revealed its presence, optical telescopes showed nothing. No glowing star, no blazing cluster. Just blackness. It was as if a voice were shouting loudly from a pitch-black room. You could hear it clearly, locate its position, even measure its strength, but you could not see the speaker. Only later, with the development of infrared astronomy, did the fog begin to lift further. Infrared light, like radio, can penetrate dust, though not quite as freely. Through infrared eyes, astronomers finally glimpsed the stars racing around the invisible center. This was the turning point. By combining observations across the spectrum radio, infrared, X-ray, a picture began to form. The galactic center was not dark at all. It was a cauldron of energy, stars whipping through space, gas clouds spiraling inward, and at the heart of it, a supermassive black hole feeding slowly on its surroundings. We did not fail to see it because it was absent. We failed because we were looking with the wrong kind of vision. Only by expanding our senses, by building instruments that could hear the universe in all its voices, did the hidden heart reveal itself. And in that revelation, we discovered the monster that holds the Milky Way together. In the 1970s, radio telescopes detected a compact blazing source of energy at the galactic center. Invisible to the eye, but screaming in radio frequencies, a cosmic beacon of raw power. It was one of the great turning points in modern astronomy. For decades, the center of the galaxy had appeared as little more than a starless void in optical light. But when researchers pointed large radio dishes toward Sagittarius, they picked up an unmistakable signal. A bright, steady emission concentrated into a region smaller than our solar system. No star cluster, no ordinary cloud of gas could generate such intensity. It was something altogether different, a voice echoing from the very heart of the Milky Way. Unlike visible light, which is easily absorbed by dust, radio waves slip through interstellar fog with ease. By tuning into these longer wavelengths, astronomers found themselves listening to the black hole's environment. And what they heard was extraordinary. Sagittarius A star was not silent. It was roaring in radio frequencies, producing more energy in a single second than the sun produces in an entire year. This roar comes from the black hole's surrounding material, not the hole itself. As gas and dust spiral inward, they form an accretion disk, a whirlpool of plasma heated to millions of degrees. The particles within it accelerate to nearly the speed of light, colliding and twisting through magnetic fields of immense strength. These interactions generate synchrotron radiation, a form of energy that shines brightest in radio waves. To human ears, it would not sound like a voice. But if we could translate its energy into sound, it would be a deafening hum, steady and unyielding. What made Sagittarius A star so puzzling, however, was its restraint. Compared to other supermassive black holes, it is unusually quiet. The monster at the center of the galaxy consumes matter sparingly, releasing occasional flares but never the blinding jets seen in more active galaxies. To some, it seemed almost dormant, like a great predator resting between hunts. Yet even in its slumber, its roar in the radio spectrum was undeniable. The discovery sparked decades of further investigation. Radio arrays across the globe were trained on the galactic center, each one peeling away another layer of mystery. Subtle variations in the emissions revealed that Sagittarius A star was not entirely steady. Bursts and flickers hinted at clouds of gas being swallowed or twisted, magnetic fields releasing sudden energy. These outbursts reminded astronomers that the black hole is not a passive anchor, but an active, dynamic engine. In time, the roar of Sagittarius A star would help pave the way for the Event Horizon Telescope, which relied on radio observations to construct the first direct image of its shadow. Without this clue, without that cosmic beacon first detected in the 1,970 seconds, humanity might still be blind to the monster at our galaxy's core. Today, whenever radio telescopes turn toward Sagittarius, they still hear the same ancient cry. A whisper from a place where space collapses, echoing across 26,000 light years, not visible to the eye but unmistakable to the instruments that listen. The quiet giant of the Milky Way speaks in radio, and the universe has never stopped listening. Matter spiraling into Sagittarius A star becomes superheated, glowing brighter than stars. Magnetic fields twist and snap, accelerating particles near the speed of light. This process begins long before matter ever reaches the event horizon. Gas clouds, dust, and even stray stars that drift too close are drawn into a vast whirlpool of gravity. Instead of plunging straight in, the material forms an accretion disk, a flattened ring spiraling endlessly toward the black hole. Friction within this disk is immense. Particles collide, compress, and heat to billions of degrees. The disk glows across the electromagnetic spectrum, shining more fiercely than entire constellations. But it is the magnetic fields that transform this region into a storm. Charged particles, trapped within the fields, spiral along invisible lines that twist and tangle as they interact with the swirling plasma. These fields can stretch, snap, and reconnect in violent bursts, releasing energy equivalent to billions of nuclear bombs. In those moments, particles are hurled outward at relativistic speeds, racing close to the speed of light. We see the effects as flares sudden outbursts of radiation in X-ray and radio frequencies. For hours, Sagittarius A star brightens dramatically, as though the monster has stirred from its slumber. Then, just as quickly, it fades back to its usual quiet glow. Each flare is a reminder that while the black hole may seem calm, beneath the surface it is anything but. It is a storm of unimaginable scale, a cosmic weather system driven by gravity, heat, and magnetism. In more active galaxies, these storms can generate jets. Colossal streams of plasma shot thousands of light years into space. Our galaxy's central black hole does not currently produce such dramatic displays. But the principle is the same. Magnetic fields act as both accelerators and sculptors, channeling energy into focused beams. It is nature's most powerful particle accelerator, dwarfing anything humanity could ever build. To grasp the scale, imagine a storm cloud here on Earth. Lightning cracks through the sky, illuminating the night for a fraction of a second. Now expand that storm to a disk of plasma millions of miles wide. Replace raindrops with atoms heated to billions of degrees. Replace lightning bolts with magnetic arcs so powerful they bend matter itself. That is the storm raging at the edge of Sagittarius A star. Even though we cannot see it directly with our eyes, the evidence is everywhere. Each time a flare reaches our instruments, it carries the signature of those magnetic tempests. Each outburst is a cosmic pulse, a heartbeat of the galaxy's core. For scientists, these events are windows into the hidden physics of extreme environments, where gravity and magnetism collide in ways still not fully understood. And yet, for all its violence, the storm is fleeting compared to the lifespan of the galaxy. These tempests rise and fall, but Sagittarius A star remains a quiet giant, occasionally flashing reminders of its strength. Its magnetic storms tell us that even silence has depth, and even the calmest of giants can roar when stirred. If the Milky Way were the size of North America, Sagittarius A star would be no bigger than a grain of sand. Yet that grain controls everything from coast to coast. The vastness of the galaxy is almost beyond comprehension. 100,000 light-years stretch from one spiral arm to another, a gulf so wide that even a beam of light would take longer than all of human history to cross. Within this immense disk swirl hundreds of billions of stars, each with their own planets, moons, and clouds of dust. Against this grand backdrop, it is easy to imagine that one small object, even a black hole, would be insignificant. And yet, the exact opposite is true. Sagittarius A star is tiny when compared to the scale of the Milky Way. Its event horizon measures only about 12 million miles across a speck compared to the galaxy's 100,000 light-year span. And still, the galaxy as a whole is bound to its gravity. Every orbit, every spiral arm, every distant star dancing at the edges of the disk owes its path to the presence of this central mass. That grain of sand is the keystone of the entire structure. To understand the comparison, imagine standing on the west coast of North America and dropping a single grain of sand onto the ground. Now imagine that grain controlling the tides of the Atlantic Ocean, the winds over the Great Plains, and the orbits of every city and mountain in between. It is a humbling reminder of just how concentrated the black hole's mass truly is. 4 million suns compressed into one invisible anchor, shaping the lives of billions of stars. Other galaxies provide even more staggering comparisons. The supermassive black hole in Messier 87 outweighs Sagittarius A star by more than 1,000-fold. Its event horizon could swallow our entire solar system with room to spare. Yet even there, the principle holds. Something tiny compared to its galaxy dictates the motion of everything within it. Across the universe, structure emerges not from visible size, but from invisible weight. And here lies the paradox. Black holes may appear small, yet their influence is immeasurable. They do not dominate by covering vast regions of space. They dominate because of the way gravity scales with mass. Their reach extends far beyond their immediate shadow. For Sagittarius A star, that reach stretches across 26,000 light-years, guiding the orbit of our own sun as surely as it guides the stars in its immediate neighborhood. When you look at the night sky, the galaxy feels infinite. The stars seem scattered without pattern. But in truth, they are all connected, moving in sync around that tiny central anchor. Just as planets orbit the sun and moons orbit planets, the galaxy itself orbits Sagittarius A star. It is the final step in the hierarchy of cosmic scales. So the next time you picture the Milky Way stretched across the heavens, remember the grain of sand at its center, small beyond belief, yet powerful beyond measure. The quiet giant whose presence gives the galaxy its shape. Stars in the outer regions orbit too fast to be held by visible matter alone. Sagittarius A star provides the gravitational anchor, preventing the Milky Way from tearing itself apart. At first glance, the galaxy seems delicate. Vast spiral arms sweep gracefully outward, their stars strung like pearls across the night. One might imagine that these arms are fragile, ready to drift apart at the slightest disturbance. After all, stars on the edges of the Milky Way move at astonishing speeds, circling the galactic core once every few 100 million years. By the laws of classical mechanics, those stars should not remain bound. The reason lies in the hidden balance of forces. Sagittarius A star provides the central mass that anchors the galaxy's rotation. Like a weight at the center of a spinning wheel, it ensures that the stars remain bound to the structure as a whole. Without it, the elegant spiral pattern would unravel, leaving behind a diffuse haze of drifting stars. But the story is more complex. Even with its 4 million solar masses, Sagittarius A star alone cannot account for the observed speeds of stars in the outer disk. Something else must contribute to the galaxy's cohesion. That something is dark matter, an invisible halo of mass that surrounds the Milky Way. Together, the supermassive black hole and the unseen envelope of dark matter provide the gravitational glue holding the system intact. The black hole anchors the heart, the dark matter stabilizes the arms. Think of the galaxy as a great cosmic dance. At the center, Sagittarius A star keeps time, its gravity providing the beat. Around it, stars and gas clouds follow the rhythm, each orbit a step in the grand pattern. If the core mass were removed, the choreography would collapse. The outer stars would drift away, and the spiral arms would lose their shape. What we see today, the graceful sweep of starlight, exists only because the hidden mass maintains the tempo. For us on Earth, this anchoring is more than an abstract concept. Our solar system itself is bound by it. At this very moment, we are racing around the galactic center at 500,000 miles per hour, part of a journey that takes 240 million years to complete a single orbit. Were the Milky Way unstable, our sun would wander off into the void, dragging Earth and the other planets with it. Life as we know it owes its continuity to the invisible tether of Sagittarius A star. It is humbling to realize that stability arises from the unseen. The stars we admire at night, the constellations that guided sailors and storytellers for millennia, are secure in their places because of a darkness we cannot see directly. The galaxy does not fly apart because a silent giant sits at its center, its gravity binding together billions of suns. Right now, the Earth, Sun, and planets are hurtling around the galactic center at 515,000 miles per hour, pulled on an orbit that takes 240 million years to complete. It is easy to imagine ourselves as still, anchored to the ground beneath our feet. The mountains seem immovable, the oceans eternal, the continents steadfast. Yet this stability is an illusion. Our entire solar system is in motion, tracing an enormous path around the heart of the Milky Way. At over 500,000 miles per hour, we are never in the same place twice. Every second carries us farther along a cosmic road we cannot see. To put that speed into perspective, Earth orbits the Sun at about 67,000 miles per hour. The International Space Station circles Earth at 17,000 miles per hour. Voyager 1, humanity's most distant probe, sails away from the solar system at 38,000 miles per hour. The Sun, along with all its planets, moons and comets, is a passenger on a much larger journey, drawn ever forward by the pull of Sagittarius A asterisk. This immense orbit is called the galactic year. It takes 240 million Earth years to complete. When the Sun last passed this point in its orbit, the age of the dinosaurs was just beginning. The continents were fused into the supercontinent Pangaea. Forests of towering ferns covered the land, and the first mammals had not yet appeared. In the span of a single galactic year, entire eras of life on Earth rise and vanish. Civilizations, species, and even mountains are temporary markers along the path of this cosmic voyage. The orbit itself is not a perfect circle, but a gently curving ellipse, weaving through the spiral arms of the galaxy. As the Sun carries us through regions dense with stars and gas, the night sky slowly changes. Over millions of years, constellations dissolve and reform, their familiar patterns shifting into new arrangements. To future civilizations, the sky we know today will be unrecognizable, a reminder that even the heavens are in constant motion. Despite the staggering speed, we do not feel it. There is no rush of wind, no shudder of acceleration. Motion through space is relative. Everything around us shares the same journey. The planets orbit the Sun as though nothing unusual is happening. Yet beyond the comfort of our local system, the truth remains. We are racing around a colossal track, bound to the center of the galaxy by the invisible tether of gravity. This realization invites reflection. Every moment of human history, every thought, Every dream has unfolded aboard a planet spinning on its axis, orbiting its star, and riding that star in turn around the galaxy. We are travelers in more ways than one, passengers on a voyage so vast it defies imagination. And though the journey is long, and the road unseen, its direction is certain, forever around the quiet giant at the heart of the Milky Way. Stars near the black hole don't follow simple loops. Their orbits precess, slowly rotating in space, tracing rosettes like petals of a cosmic flower, a direct test of Einstein's theory. To most of us, an orbit seems like the simplest shape in the universe, a circle or perhaps an ellipse. Planets around the sun, moons around planets, even comets with their stretched paths all return again and again to the same trajectory. But near a supermassive black hole, things are different. Space-time itself is warped, bent, and curved in ways Newton could never have imagined. The result is a new kind of orbit, one that does not close neatly but slowly drifts, like a spinning flower unfolding petal by petal. This effect is called orbital precession. It was first noticed with Mercury, the innermost planet of our solar system. Its path around the Sun shifts slightly with each revolution, tracing a rosette pattern instead of repeating perfectly. For centuries, astronomers puzzled over this anomaly. Only Einstein's general relativity provided the answer. Space-time around the Sun is curved, and that curvature nudges Mercury's orbit forward. What happens around Sagittarius A star is the same effect, but magnified on an unimaginable scale. The star S2 once again became the perfect test case. Every 16 years, it completes an elongated orbit around the black hole. Careful measurements revealed that its path does not retrace itself. Instead, each time S2 swings closest to Sagittarius A star, its orbit has rotated slightly, like the petal of a flower opening into a new direction. Over thousands of years, the orbit would trace a full blossom, a cosmic rosette written into the night. This drifting orbit is not a flaw, but a triumph. It confirms, with elegant precision, that Einstein's vision of gravity is correct. Gravity is not a force pulling through empty space, but the bending of space and time themselves. Near Sagittarius A star, space-time is so warped that even the stars cannot repeat their steps exactly. They are like dancers moving on a stage that shifts beneath their feet. Their paths altered by the very fabric of the universe. For astronomers, this precession is more than just beautiful. It is a laboratory. By studying how much the orbit rotates, scientists can test the predictions of relativity under extreme conditions. Every deviation, every shift, either confirms the theory or hints at new physics waiting to be uncovered. Sagittarius A star, in this sense, is not just a black hole. It is a cosmic experiment constantly running, with stars as the instruments and space-time as the canvas. When we imagine these rosette orbits, we should not think of rigid geometry but of living patterns. The stars carve flowers into the night, slow blooms opening over centuries and millennia. Each petal is a revolution, each shift a whisper of spacetime's curvature. The black hole at the center does not just pull stars inward, it sculpts their paths into art, delicate and precise. And so, in the heart of the galaxy, flowers bloom not of petals or color, but of orbits, geometry, and gravity itself. During S2's closest approach, astronomers measured its light stretching and reddening, proof that time itself slows under the weight of Sagittarius A star's gravity. This phenomenon, known as gravitational redshift, is one of the clearest demonstrations of Einstein's general relativity. When light escapes from a strong gravitational field, it loses energy. Because photons cannot slow down, they always move at the speed of light. They lose energy by changing color, shifting toward the red end of the spectrum. For astronomers watching S2 swing past Sagittarius A star, this redshift was not just a subtle effect. It was a direct measurement of time itself running more slowly in the star's frame of reference. Imagine two clocks, one ticking on Earth and another carried aboard S2 as it races around the black hole. To someone standing on the star's surface, the clock would seem normal, each second passing as it always has. But for observers on Earth, that same clock would appear to run slightly behind. Each tick would take a fraction longer to arrive. Time near Sagittarius A star is stretched, elongated by gravity, while our own time flows more quickly. This was no thought experiment. In 2018, scientists used the Very Large Telescope in Chile to measure S2's spectrum during its closest pass. The data showed unmistakable evidence of gravitational redshift. It was the first time this effect had been observed so clearly in a star orbiting a supermassive black hole. For physicists, it was a triumph. A century-old prediction of relativity confirmed by nature's own cosmic laboratory. The implications are staggering. It means that time is not universal. Seconds, minutes, and hours do not pass equally everywhere. They are woven into the fabric of space-time, and that fabric bends under the influence of mass. Near Earth, we already adjust for this effect in our daily lives. GPS satellites must account for time dilation, both from their speed in orbit and from Earth's gravity, or our navigation systems would drift by miles each day. If such corrections are needed here, how much more dramatic must the effect be around Sagittarius A star? To put it another way, if you could hover safely near the black hole and then return to Earth, you would find that more time had passed here than for you. Days, years, even centuries could slip by outside, while only moments passed for you close to the horizon. Science fiction often calls this time travel. But in truth, it is a natural consequence of relativity. Gravity bends not only space, but also the very rhythm of existence. For astronomers, observing time dilation in action is more than a curiosity. It is a vital test of physics under extreme conditions. By watching how stars like S2 behave, we gain confidence that Einstein's equations remain valid even in the strongest gravitational fields we can observe. And so, the star's reddened light is more than a glow in the darkness. It is a signal, a cosmic clock revealing that time itself is pliable, reshaped by the gravity of a monster 4 million times the mass of our Sun. Beyond the event horizon lies the singularity, a point where density becomes infinite and the known laws of physics break down completely. This is the region we cannot see, the space forever hidden from observation. Once matter crosses the event horizon, it cannot send back information. Light itself is trapped, and with it, every clue about what unfolds within. What we have instead are equations, Einstein's general relativity predicting the structure of space-time, and quantum mechanics describing the behavior of the smallest particles. But here, at the singularity, those two frameworks clash. Relativity insists that gravity compresses matter to infinite density, while quantum theory insists that infinities cannot exist. It is the deepest riddle in modern physics. The singularity is not a place in the conventional sense. It has no surface, no size, no definable shape. It is a point where the curvature of space-time becomes so extreme that our equations can no longer handle it. Imagine a map that works beautifully to chart continents, mountains, and oceans, but fails when it reaches the edge of the world. The singularity is that edge, not an object, but a breakdown of our understanding. What would happen to anything that falls inside? For small black holes, tidal forces grow so extreme near the horizon that objects are torn apart long before reaching the center. This process, sometimes described as spaghettification, stretches matter into long threads of atoms. But Sagittarius A star, being supermassive, offers a stranger fate. A spacecraft could cross without immediate destruction, plunging deeper into the darkness before the forces grew overwhelming. Only near the singularity itself would the pull become absolute, compressing matter to an unknowable state. Some physicists speculate that the singularity may not exist as Einstein described. Perhaps quantum mechanics intervenes, creating a dense but finite core. Others propose that information is not destroyed inside a black hole but encoded on its horizon in a kind of cosmic ledger, a concept known as the holographic principle. Still others imagine black holes as gateways, connected by wormholes to distant parts of the universe or even to entirely different universes. These remain possibilities, not certainties, because no observation can yet reach past the horizon. For now, the interior of Sagittarius A star is a domain of speculation, a frontier where science and philosophy meet. What we do know is this: the singularity represents a challenge, a signal that our current theories are incomplete. Somewhere in the marriage of general relativity and quantum mechanics lies the answer. A theory of quantum gravity that will finally explain what happens when matter is compressed beyond recognition. Until then, the inside of a black hole is a mystery written in silence. Beyond the horizon lies a place where our maps end, where time and space themselves collapse, and where the universe keeps its most closely guarded secret. Though measured at 4 million solar masses, the true influence of Sagittarius A star extends far beyond. Its gravitational reach stretches across thousands of light years. When we hear that the black hole at the center of the Milky Way weighs 4 million times as much as the Sun, it sounds like a complete description. But numbers can be deceptive. That figure refers to the mass locked within the event horizon itself, the compact core hidden from sight. In reality, the presence of Sagittarius A star is felt across a region unimaginably larger than its 12 million mile wide shadow. Its gravity extends outward across the bulge of the galaxy, influencing stars, clusters, and gas clouds for thousands of light years in every direction. Consider our solar system. The Sun's gravitational hold stretches far beyond the orbit of Neptune into the Oort cloud, where icy bodies drift hundreds of billions of miles away. Even there, the Sun's pull dominates, gently binding those distant objects. Sagittarius A star functions in much the same way, but on a galactic scale. It is not merely a point mass at the center, it is the anchor for the Milky Way's entire structure. Some astronomers even argue that the true footprint of the black hole cannot be separated cleanly from the galactic bulge around it. The bulge, a dense sphere of stars clustered near the core, contains tens of billions of solar masses, and many of those stars orbit in resonance with the black hole itself. Together, they create a gravitational environment that shapes the galaxy's inner architecture. Remove the bulge, and the black hole's influence would feel incomplete. Its reach is not only physical but also temporal. Over billions of years, the black hole has sculpted the growth of the Milky Way. When it was younger, Sagittarius A star may have been far more active, consuming vast amounts of gas and releasing powerful jets of energy. Evidence suggests that in the distant past, it lit up the galaxy's core with radiant outbursts, leaving behind faint traces still visible today, enormous bubbles of gamma rays extending above and below the galactic plane. These are signs that its influence once reached far beyond its current quiet state. Even now, stars thousands of light years away orbit the center with Sagittarius A star as their anchor. The Sun itself is one of them, completing a galactic lap every 240 million years. From such a distance, the black hole is invisible and unremarkable, yet its pull is constant, guiding our journey as surely as it guides the nearest stars whipping past its horizon. So, while we measure Sagittarius A star at 4 million solar masses, the truth is that its domain cannot be captured by a single number. Its presence ripples across the Milky Way, shaping both its structure and its history. It is larger than we think, not because its event horizon is underestimated, but because its influence is immeasurable, stretching across space and time to touch every corner of our galactic home. When clouds of gas fall inward, they flare brilliantly before vanishing. These outbursts send X-rays and radio bursts echoing across space, brief glimpses of its feeding. Black holes are often imagined as silent, insatiable mouths, swallowing everything in total darkness. But in reality, the act of feeding is anything but quiet. Matter falling towards Sagittarius A star does not simply disappear. Before it crosses the event horizon, it is accelerated, compressed, and heated to extraordinary extremes. The gas glows with such intensity that it outshines entire star systems, releasing flashes of high-energy radiation. These are the echoes of falling matter, the last signals we receive before the black hole claims it forever. Astronomers detect these flares in both X-ray and radio wavelengths. They appear suddenly, often lasting only a few hours, then fade back into silence. Each burst tells a story of some fragment of matter, perhaps a drifting gas cloud, perhaps the outer layers of a star nudged too close, spiraling inward on its final descent. The process is violent. Atoms collide at near-light speeds, magnetic fields twist and snap, and the resulting release of energy radiates across the galaxy. In 2019, one such flare caught astronomers' attention. For a brief time, Sagittarius A star became 75 times brighter in infrared light than usual. It was as if the black hole had suddenly awakened, flashing a warning across space before retreating back into its quiet state. Events like these are rare, unpredictable, and invaluable, for they offer fleeting glimpses into the dynamics of matter at the edge of the abyss. The physics behind these echoes is as fascinating as it is complex. Gas falling inward does not always plunge directly into the horizon. Instead, much of it forms a swirling disk where friction and turbulence dominate. Only a fraction is consumed. Some is flung outward in arcs of radiation and jets of particles. These echoes are not merely byproducts. They are the black hole's announcement of its presence, ripples of energy that carry news of its hunger across the cosmos. For Earth-bound observers, these signals are faint but measurable. Space telescopes tuned to X-ray and radio wavelengths capture them, adding puzzle pieces to our understanding of Sagittarius A star. Each flare acts like a cosmic postcard, stamped with the conditions of its origin. Temperature, density, and the ferocity of the magnetic storms surrounding the black hole. From these clues, scientists can reconstruct a picture of events occurring in a place where no light escapes. Even when Sagittarius A star is quiet, faint ripples of radiation hum in the background. This gentle glow is the signature of material constantly drifting inward, a slow rain of gas falling into the central well. But when larger clouds approach, the silence breaks into sudden storms of brilliance. For hours, the black hole announces its meal, before swallowing it whole and returning once again to its calm facade. These echoes remind us of a profound truth. Even in darkness, nothing is truly silent. The feeding of Sagittarius A star resonates across the galaxy, and though the meal is lost to us forever, its light lingers just long enough to tell the story. Despite its terrifying pull, Sagittarius A star is unusually quiet compared to other supermassive black holes. It consumes matter only occasionally, like a predator resting between hunts. In the grand zoo of galaxies, some black holes are voracious feeders. They consume entire stars, devour massive clouds of gas, and unleash brilliant jets of plasma that stretch thousands of light years. These are the so-called quasars, galaxies whose central black holes blaze with such intensity that they outshine all the stars combined. Compared to these cosmic beacons, the black hole at the center of our Milky Way seems almost shy. Sagittarius A star glows faintly in X-ray and radio, and only rarely bursts into dramatic flares. It spends most of its time in a state of quiet hunger, waiting patiently for its next meal to stumble too close. Why is it so subdued? The answer lies in its environment. Unlike more active galaxies, the center of the Milky Way is relatively calm. There are stars, yes, and clouds of dust and gas, but not in the enormous quantities required to fuel constant feeding. Sagittarius A star is like a predator in a land where prey is scarce, It waits, conserving its energy, feeding only when chance delivers a meal into its grasp. When matter does arrive, the results can be spectacular. Clouds of gas, drawn from disrupted stars or wandering interstellar streams, swirl inward and heat to millions of degrees. For a few hours or days, the black hole awakens, flaring brightly in X-rays and infrared light. These brief episodes are reminders of its latent power, flashes of activity that hint at what Sagittarius A star might look like if it were surrounded by richer fuel supplies. Astronomers have found evidence that in the past, our galaxy's central black hole may have been much more active. Observations of giant gamma-ray bubbles stretching above and below the Milky Way suggest that several million years ago, Sagittarius A star went through a feeding frenzy, releasing energy powerful enough to reshape the galactic environment. Today, however, it slumbers, its appetite reduced to small occasional snacks. This quietness has been a gift to Earth. If Sagittarius A star behaved like a quasar, the radiation pouring from the galactic center could sterilize vast regions of space, making life far less likely to survive in the Milky Way. Instead, our black hole's modest appetite allows planets like Earth to orbit peacefully, shielded from destructive outbursts. The same predator that could ravage entire systems rests quietly enough to let life flourish. Still, the potential remains. Sagittarius A star could stir again. If a massive gas cloud were to wander too close, the black hole could flare into brilliance once more, reminding us of its true power. For now, though, it waits, a giant predator conserving its strength, a cosmic hunger biding its time. It is this paradox, immense power, wrapped in quiet restraint, that makes Sagittarius A star so intriguing. It is not a quasar, not a roaring monster, but a patient hunter, silent most days, yet capable of devouring stars when opportunity arises. If Earth orbited where S2 passes, the black hole would fill half our sky. Radiation storms would burn away our atmosphere, leaving no chance for life to exist. The galactic center is a very different environment from the quiet neighborhood we inhabit. Here, in our solar system, stars are comfortably spaced, with light years of emptiness between them. But near Sagittarius A star, the stars crowd together in dense clusters, separated by mere fractions of a light year. The night sky would blaze with thousands of suns, each one brighter than the stars we see from Earth. Their combined light would make darkness rare, bathing the sky in a perpetual glow. From such a vantage point, Sagittarius A star itself would be a dominating presence. The event horizon, 12 million miles across, would loom enormous in the heavens, a black void rimmed by a distorted halo of light. It would not twinkle like a star, nor shine with steady brilliance. Instead, it would warp the background, bending starlight into rings and crescents, a shifting mirage painted across the sky. To stand on a planet in that region would be to live beneath an ever-present reminder of gravity's most extreme expression. But beauty would come at a terrible cost. The radiation near the galactic core is far more intense than in our quiet outskirts. X-rays and gamma rays pour from the black hole's accretion disk whenever matter falls inward. Powerful magnetic fields whip particles into near light-speed jets, bathing the surrounding space in lethal radiation. Any planet orbiting there would find its atmosphere stripped away, its surface scorched. Even deep oceans would boil beneath the constant bombardment. Life, as we know it, would be impossible. The gravitational environment itself would pose other dangers. Stars move at breakneck speeds, their orbits twisted into eccentric ellipses. Close encounters between stars would be common, destabilizing planetary systems. Some planets would be flung into interstellar space, lost forever. Others might spiral inward, doomed to destruction. It is a cosmic neighborhood where permanence is rare and chaos is the rule. Astronomers sometimes describe the galactic center as a stellar zoo. Exotic stars crowd the region, massive blue giants, tightly bound binaries, and pulsars ticking like cosmic clocks. Some stars even orbit so close to Sagittarius A star that they complete their revolutions in mere decades. To live among them would mean watching constellations rearrange themselves in a human lifetime, the night sky shifting in ways unimaginable from Earth. For us, safely distanced in the spiral arms, the galactic center is a place of study, not of habitation. It is a laboratory for physics, a stage where Einstein's theories play out with dramatic clarity. But it is not a place to call home. Our position, 26,000 light-years away, gives us the perfect vantage point. Close enough to observe, far enough to survive. So, when we gaze towards Sagittarius, we should be grateful. The black hole may hold our galaxy together, but it does so from a distance that allows us to exist. The galactic center up close is a place of awe and terror, beautiful to imagine, but deadly to endure. Other galaxies host monsters billions of times more massive than Sagittarius A star, yet ours feels intimate, a smaller, quieter giant at the heart of our cosmic home. In the grand scale of the universe, Sagittarius A star is modest. At 4 million solar masses, it pales in comparison to the true titans. The black hole at the center of galaxy M87, for instance, weighs in at an astonishing 6.5 billion solar masses. Its event horizon is so vast that it could swallow our entire solar system whole, with room to spare. Quasars powered by such giants blaze like cosmic lighthouses, their light visible across billions of light-years, often outshining every star in their host galaxies combined. By contrast, Sagittarius A star is subdued, almost humble. It does not dominate the night sky, nor does it drench the galaxy in radiation. Instead, it sits quietly at the core, feeding only occasionally, leaving the Milky Way's spiral arms free to nurture stars and planets. This quietness is what makes it feel personal. It is our black hole, not a distant quasar studied from afar, but a giant we orbit, a presence we live with. And yet, its smaller size offers unique advantages for science. The orbits of nearby stars, such as S2, are measurable within a human lifetime. Around larger black holes, orbital periods stretch into centuries or millennia, far beyond the reach of a single generation of astronomers. Sagittarius A star allows us to witness entire orbits unfold, to test Einstein's theories in real time. Its intimacy gives us insight that the larger, more distant giants cannot provide. Still, the comparison humbles us. Imagine a hierarchy of black holes. At the bottom are the stellar mass remnants of collapsed stars, weighing a few times the mass of the Sun. In the middle are Sagittarius A star and its kin Supermassive, yet on the smaller end of the scale. At the top sit the ultramassive black holes, true monsters billions of solar masses strong, shaping the fate of entire clusters of galaxies. Ours is somewhere in between. A middleweight colossus, powerful enough to anchor the Milky Way, but gentle compared to the universe's brightest beacons. Astronomers wonder why black holes vary so much in size. Did they all begin small, feeding steadily over cosmic time? Or did some galaxies merge again and again, funneling gas into their centers until their black holes ballooned to unimaginable proportions? Sagittarius A star may offer clues. Its quietness today could be the echo of a more active past, a reminder that even small giants can roar under the right conditions. For now, we can be grateful that ours is restrained. Were Sagittarius A star a billion solar mass monster, the Milky Way might be a harsher, less hospitable place. Instead, it remains a quiet guardian, balancing gravity without overwhelming its surroundings. In the end, the giants of the cosmos remind us that scale is relative. To compare billions of solar masses with millions is to measure infinities against infinities. And yet, for us, Sagittarius A star is the most important of them all. It may not be the largest, but it is ours, the quiet heart of our galactic home. The glowing ring revealed by the Event Horizon Telescope wasn't just an image. It was proof that general relativity, written over a century ago, had predicted reality with stunning accuracy. When Albert Einstein first introduced general relativity in 1915, the world was still adjusting to the idea that space and time were not fixed backdrops, but flexible dimensions shaped by mass and energy. His equations suggested something extraordinary: that gravity could bend light, warp time, and even create regions where nothing, not even light itself, could escape. At the time, such predictions seemed almost too bold to believe. For decades, physicists debated whether black holes were real or merely mathematical curiosities. They existed in the equations but remained invisible to telescopes. Astronomers had indirect evidence stars orbiting empty space, bursts of radiation from unseen sources but no direct confirmation. That changed in 2019 with the first image of the supermassive black hole in galaxy M87. And again in 2022 with the unveiling of Sagittarius A star. Both images showed precisely what Einstein's theory foretold. The photograph of Sagittarius A star was particularly powerful because of its intimacy. To see its silhouette was to peer directly at the heart of our home galaxy, the place around which our Sun, Earth, and every star we see in the night sky revolves. The glowing ring itself carries layers of meaning. It is formed by photons trapped in orbit, circling the black hole before some escape toward Earth. Their paths are distorted into a near-perfect circle, the photon sphere predicted by relativity. Inside the ring lies the shadow, the projection of the event horizon, where gravity's pull is absolute. The size and shape of that shadow matched Einstein's equations almost perfectly, a triumph for theoretical physics. This agreement is remarkable because relativity has now been tested in environments ranging from Mercury's orbit to the edge of a supermassive black hole. Each time, the theory holds true. It tells us that the universe behaves according to the rules Einstein wrote more than a century ago, even in places far more extreme than he could have imagined. But the first photo proved more than equations. It showed the power of human collaboration. Hundreds of scientists, working across continents, linked radio telescopes into one Earth-sized eye. They synchronized data with atomic clocks, processed petabytes of information, and reconstructed a picture from the whispers of radio waves collected across the globe. The result was not only a scientific milestone but also a testament to human curiosity and persistence. In the glowing ring of Sagittarius A star, we see both the power of nature and the accuracy of human thought. A century-old theory became a photograph. What was once imagination became reality. And in that image, we glimpse the strange truth of our universe, that space and time themselves bend to the will of gravity. If you carried an atomic clock toward the event horizon, it would tick more and more slowly. To outside observers, it would eventually appear frozen, forever balanced at the edge of eternity. This is one of the strangest predictions of Einstein's theory of general relativity. That time itself is relative, warped by gravity just as surely as space is bent. An atomic clock, the most precise timekeeper we know, measures each second with vibrations of atoms that never waver. On Earth, such a clock might lose less than a second over the entire age of the universe. Yet even this perfect instrument cannot escape the distortions of space-time. As you carried the clock closer to Sagittarius A star, it would continue to tick normally from your perspective. The rhythm of its pulses would feel unchanged, each second arriving with steady certainty. But for those watching from a safe distance, the story would be different. They would see the clock slowing. The steady ticks would stretch farther apart, seconds lengthening into minutes, minutes into hours. The closer the clock drew to the event horizon, the slower it would seem to move. At the threshold itself, it would appear to stop entirely, frozen in place for all eternity. This effect is not illusion, it is the true bending of time. Gravity does not merely hold planets in orbit or bend the path of light. It changes the very pace of existence. In strong gravitational fields, time runs more slowly. Near Earth, the difference is tiny satellites in orbit must adjust for it, but we never notice in daily life. Near a black hole, the effect becomes profound, stretching seconds into infinities. The paradox is that both perspectives are valid. To you, falling with the clock, nothing unusual happens. Your seconds remain seconds. You pass the horizon without noticing anything special. But to the distant observer, you never cross at all. Your image hovers just above the event horizon, fading slowly as light grows weaker and redder, until it disappears. Two realities, both true, both describing the same event. This concept challenges our deepest intuitions. We are taught to think of time as universal, a steady drumbeat against which the universe unfolds. But relativity reveals that time is local, personal, and relative to gravity. What seems eternal to one observer may be fleeting to another. If you could somehow return from this journey, impossible though that is, you would find the universe transformed. Eons might have passed outside while only hours passed for you. Civilizations would rise and fall. Stars would burn out. To approach the edge of a black hole is, in a sense, to step into the future, carried forward by the slowing of your own clock. And yet, there is a limit. Once you cross the horizon, no return is possible. The frozen image of the clock remains forever outside, a shadow for others to see, while the true clock, the one in your hand, continues its steady march into darkness. A timepiece at the edge of forever, ticking faithfully as the universe rushes on without you. From Earth, Sagittarius A star's event horizon spans just 50 microarc seconds across. If your eyes were sharp enough, you could just barely spot it if it were the size of an orange on the moon. That tiny measurement, 50 millionths of an arcsecond, is almost beyond imagination. An arcsecond itself is 1/3, 600 of a degree, and here we are talking about a fraction of that already minuscule slice of the sky. To put it in perspective, if you held a human hair at arm's length, its width would appear thousands of times larger than the shadow of Sagittarius A star. It is the smallest, most elusive target ever captured by astronomy, a needle of darkness hidden in the cosmic haystack. And yet, despite its diminutive appearance, this shadow is the silhouette of a giant. Its event horizon is 12 million miles across, large enough to swallow Mercury's orbit. The only reason it looks so small to us is distance. At 26,000 light-years away, even a monster of this scale shrinks to the apparent size of an orange left on the lunar surface. What we see is not the hole itself, but its gravitational shadow, magnified and sharpened by light bending around it. Detecting something so faint and so small is one of the greatest achievements of modern science. No single telescope on Earth has the resolution to glimpse an object 50 microarc seconds wide. Instead, astronomers linked observatories across the globe to create the Event Horizon Telescope, effectively turning our planet into one giant dish. By synchronizing their signals with atomic clocks, they built an Earth-sized eye capable of the precision required. It was this technique that produced the famous image of the glowing ring around Sagittarius A star, a picture assembled from data gathered at multiple points on the globe. This feat is even more impressive when you consider how turbulent the galactic center is. Gas clouds swirl, stars flare, and plasma flickers in the black hole's accretion disk. The image we saw was not a snapshot in the conventional sense, but a carefully reconstructed average, pulling order out of chaos. And still, the result matched theory almost perfectly. A round shadow, ringed by light, exactly as Einstein's equations predicted. The comparison to everyday scales is humbling. If the black hole's shadow were projected into the sky, it would cover less area than a tennis ball viewed from thousands of miles away. If you placed a coin on the surface of the Moon, it would still appear larger than Sagittarius A star. That we can not only detect such a thing but also resolve its shape is a testament to the ingenuity of human science. So when you look toward the constellation Sagittarius, know that hidden there is a shadow so small it defies human perception, yet so massive it anchors our entire galaxy. Its size in our sky may be no larger than an orange on the Moon, but in reality, it is the doorway to eternity, a cosmic horizon that marks the point of no return. The black hole's pull stretches stars like taffy. These tidal forces would tear apart planets, moons, and even entire solar systems that wander too close. Gravity, though invisible, is not uniform. Even here on Earth, its pull varies slightly from your head to your feet. The difference is so tiny you never notice it, but near a black hole the variation becomes extreme. These differences in pull are called tidal forces, and they grow stronger the closer you approach the event horizon. In the grip of Sagittarius A star, they are capable of shredding matter at the atomic level. Imagine a planet falling toward the black hole. The side closer to the event horizon feels a much stronger pull than the side farther away. The planet is stretched along the line of gravity, while its width is squeezed inward. As the descent continues, the planet elongates into a distorted shape, pulled thinner and thinner, until it unravels into streams of debris. This process, dramatically nicknamed spaghettification, is gravity's most ruthless trick. Stars are not immune. In rare but spectacular events known as tidal disruption events, entire stars are torn apart by supermassive black holes. Gas ripped from their surfaces forms glowing streams that spiral into accretion disks, releasing bursts of energy visible across billions of light years. The star itself vanishes, shredded into ribbons of plasma before being consumed. Such events remind us that black holes are not only quiet anchors but also cosmic predators, reshaping the lives of anything that ventures too close. In Sagittarius A star, the scale is slightly different from smaller black holes. Because its event horizon is so large, tidal forces at the edge are less violent. A spacecraft crossing the horizon might not be torn apart instantly. Instead, it could descend deeper before the forces reached fatal levels. But ultimately, the result would be the same. Everything stretched, distorted, and compressed into nothing recognizable. The difference is only one of timing. These tidal forces extend outward as well, shaping the orbits of nearby stars. Astronomers watching the galactic center see stars whip around in elliptical paths, their speeds dictated not only by the black hole's gravity, but also by the subtle tugs of tides. The very motion of these stars provides the evidence for Sagittarius A star's mass, the cosmic fingerprints of its invisible hand. Even across thousands of light years, the black hole's tidal influence is felt. It organizes star clusters, nudges gas clouds, and sculpts the structure of the inner galaxy. What happens on the smallest scales a planet stretched? A star shredded echoes on the grandest scales of galactic architecture. The tides of space-time remind us that black holes are not static voids. They are dynamic engines, twisting matter and light, pulling apart the fabric of the universe itself. And while the phrase "stretched like taffy" may sound whimsical, the reality is awe-inspiring, terrifying, and deeply beautiful. A force so absolute that it reshapes stars, systems, and space-time itself. Our orbit around the galactic center is stable. The black hole will never directly swallow the solar system. But over trillions of years, galaxies change, and nothing is truly permanent. Right now, Earth and the Sun are safe. At 26,000 light-years away, we are far beyond the black hole's immediate grasp. Our solar system's orbit is well within the stable confines of the Milky Way, taking 240 million years to complete a single revolution. Sagittarius A star exerts a steady pull, but no more so than the gravity of the entire galaxy combined. For all practical purposes, our fate is not to be consumed. At least, not anytime soon. But the universe is a restless place, and cosmic timescales dwarf the lives of stars and planets. Galaxies collide, spiral arms shift, and gravitational tugs slowly alter orbits. The Milky Way itself is on a collision course with the Andromeda Galaxy, an event expected to occur in about 4 billion years. When that merger unfolds, black holes at the centers of both galaxies will spiral inward and eventually merge into a larger, even more massive singularity. The Sun and Earth may still survive that upheaval, but our trajectory could shift dramatically, carrying us closer to or farther from the galactic core. Even if we remain distant, the story does not end there. Over trillions of years, stars will exhaust their fuel, galaxies will thin out, and orbits will destabilize. Some systems will be flung into intergalactic space, while others will slowly spiral inward toward the central black hole. Over unimaginable stretches of time, Sagittarius A star and black holes like it may become the final collectors of matter, devouring whatever remains as the universe grows darker and colder. On human timescales, however, these possibilities are so remote as to feel like eternity. Our species has existed for only a brief flicker of cosmic time, and civilizations rise and fall in mere thousands of years. Against the backdrop of trillions of years, the question of whether Sagittarius A star might one day consume us becomes more a matter of philosophy than physics. There is also a poetic symmetry in this. Black holes are not predators lurking with intent. They are simply gravity made absolute, shaping the paths of everything around them. Just as the Earth will one day be consumed by the Sun when it swells into a red giant, so too could the galaxy, in the fullness of time, be reshaped or even devoured by its central anchor. It is less a matter of if, and more a question of when and on what timescale. For now, though, we remain passengers on a safe and stable orbit. Sagittarius A star will not reach out and drag us inward. It is our companion, not our doom, at least within the lifetime of stars. Beyond that, the universe itself will decide our fate in collisions, in mergers, and in the slow march of cosmic time, where permanence is only an illusion. Every orbit of the Sun, every ancient star in the night sky, every spiral arm of the Milky Way owes its shape and rhythm to the presence of Sagittarius A star. The galaxy is not random. Its graceful spiral arms, its central bulge, and its glowing disk all exist in harmony because of an unseen conductor at the core. Sagittarius A star is that conductor, keeping time for billions of stars. It is easy to think of our solar system as isolated, drifting freely in space. But this is not true. Every orbit we take around the Sun, every season and every year, unfolds against the deeper rhythm of our orbit around the galactic center. This binding has shaped the history of our planet in ways we are only beginning to understand. As the Sun carries us around the galaxy, we pass through dense star fields, cross spiral arms, and drift through regions rich with gas and dust. Some scientists even speculate that these galactic encounters may influence life on Earth, stirring up comets from the Oort cloud, sparking bursts of impacts that leave their mark in craters and extinctions. The galaxy is not just a backdrop, it is an environment, and Sagittarius A star is at the center of it all. The ancient stars we see at night also tell this story. Many of them are billions of years old, older even than the spiral arms in which they reside. Yet all of them, young and old alike, are linked in their orbits around the black hole. Their light, which guided explorers and inspired myths, is part of a greater choreography set in motion by the Milky Way's gravitational anchor. Even the spiral arms themselves owe their shape to this central presence. Density waves ripple through the galactic disk, gathering stars into the luminous spirals we see from afar. These waves are stabilized by the mass at the center, by the invisible grip of Sagittarius A star. Without it, the arms would lose their coherence, and the galaxy would scatter into a formless haze of stars. The beauty we admire in photographs of the Milky Way exists because of the darkness at its core. For us, this perspective is humbling. Every journey humanity has ever made, across oceans, across continents, into orbit, has taken place within the larger journey of our solar system around Sagittarius A star. We have never left its influence, nor will we. Even as we send spacecraft beyond the edge of the solar system, they remain passengers on the same galactic voyage. The black hole's gravity is the one constant in all our travels. It is strange, perhaps, to think of something so destructive as a source of connection. But that is the paradox of Sagittarius A star. It holds together what would otherwise drift apart. It unites billions of stars, countless planets, and even us fragile beings on a small world, all bound in orbit around a single point of darkness. Though it seems impossibly large, Sagittarius A star is just one of countless black holes across the cosmos. It is our monster, our anchor, our quiet reminder of the strangeness at the heart of existence. At 4 million solar masses, Sagittarius A star dwarfs anything we can imagine on human scales. It swallows light, bends time, and holds an entire galaxy in its grip. And yet, when placed beside the true giants of the universe, it seems almost modest. Supermassive black holes billions of times the mass of the Sun blaze in the hearts of quasars, their jets reaching across intergalactic space. Compared to them, our black hole is a middleweight vast to us, but small in the company of cosmic titans. Still, size is only part of the story. What makes Sagittarius A star remarkable is its relationship to us. It is the black hole we can study most closely. The one we can weigh by watching stars orbit. The one we can image with an Earth-sized telescope. It is our cosmic neighbor, the shadowy core of the galaxy we call home. In its silence, it offers something the larger, more distant monsters cannot: intimacy. The universe may be filled with black holes, from the stellar mass remnants of dying suns to the gargantuan anchors of galaxies. But Sagittarius A star is the one that has shaped every moment of Earth's history. It is the reason our galaxy holds together, the reason the spiral arms remain in place, the reason our sun moves through space on its vast orbit. Without it, the Milky Way would not be what it is, and neither would we. Black holes are often imagined as destroyers, but they are also creators of structure. They bind galaxies, regulate star formation, and shape the evolution of cosmic landscapes. Sagittarius A star is no exception. Its presence has guided the Milky Way for billions of years, influencing the environment in which life eventually arose on Earth. In that sense, its shadow touches us more deeply than we might ever realize. And yet, for all we know, questions remain. What lies within the event horizon? How do black holes grow to such immense sizes? Are they portals to something beyond our universe, or simply the most extreme expression of gravity? Sagittarius A star does not answer these questions directly, but it gives us the best chance to explore them. Every orbit we measure, every flare we record, every photon we capture from its ring of light brings us closer to understanding. So while Sagittarius A star may be a tiny giant compared to others in the cosmos, it is our giant, our monster, our anchor. Its existence reminds us that the universe is stranger, larger, and more mysterious than we can ever fully comprehend. The same black hole that bends the paths of stars bends our path as well, carrying us forward on a journey around the galaxy, a quiet companion, and a reminder that even in the vastness of the universe, we are part of something extraordinary. And so, our journey comes to an end. From the hidden heart of the galaxy to the quiet giant that keeps the Milky Way bound together, we have followed the story of Sagittarius A star, a monster made not of fire and fury, but of silence and gravity. We have seen how it weighs 4 million suns, how it bends light, slows time, and sculpts the very shape of the stars above us. We have traced the dances of stars around its shadow, watched flares of falling matter echo through the galaxy, and stood in awe of the first photograph of its glowing ring. Each discovery, each measurement, has confirmed a truth Einstein wrote more than a century ago: that space and time are not fixed, but fluid, and that black holes are their most mysterious expression. And yet, for all its strangeness, Sagittarius A star is also familiar. It is the center of our galaxy, the anchor of every orbit, the quiet companion in all our cosmic journeys. Without it, the Milky Way would scatter. With it, the galaxy holds its shape, and we are carried safely along our path. In the vastness of the universe, where some black holes weigh billions of suns, ours may seem small, but it is our giant, our shadow, our reminder that we are part of something infinitely larger than ourselves. So tonight, as you drift into rest, let this thought linger. You are lying on a small world, orbiting a gentle star, and together, you and every star you see are circling a quiet giant at the center of the Milky Way. You are part of this great cosmic dance, fragile, fleeting, yet deeply connected to the fabric of the universe. Rest now, with gratitude, with wonder, and with peace. The galaxy will keep turning. Sagittarius A star will keep watch. And tomorrow, the stars will still be waiting.